Hi everyone, thanks for joining this joint webinar between SimScale and Onshape. Today we're going to be looking at an automotive design case where we're basically going to show you how you can complete your design and be done in 60 seconds. I've got the pleasure of hosting you today. My name is Steve Lene. I lead the application engineering team and our partnerships at SimScale. And I've got the pleasure of being joined by Nacho Martos from Onshape today and Richard Schuler from SimScale. Nacho is a customer marketing manager at Onshape. And at Onshape, he influences growth and strategic marketing initiatives. And Richard Schuler has a background in applied mathematics engineering, and he's a member of the product management team at SimScale. So a couple of housekeeping items before we get started. You will all remain on mute throughout this presentation, but that doesn't mean that you can't engage with us. Please do use the GoToWebinar functionality to ask questions as we go through, and we will address those questions at the end. I will put the questions to the team and we'll be very happy to answer those for you today. Also, if you haven't noticed already while you've been waiting, there is a handout available for the presentation today. You can also access that through GoToWebinar. If you press the handouts drop down, you'll be able to access that. Okay, so it's great to see so many of you here, and let's get started today. So why are we here? Well, I want to position what we're going to talk about today in terms of the problems that we see our automotive clients are facing today. On the screen here, you can see an example of some of our automotive clients at SimScale. And what we're hearing from these customers is that they're really challenged by RFP response times and getting their products to market fast enough. So many of them are saying that their development timelines have significantly shrunk because of competition. And something that we're hearing a lot is that RFQ responses are now expected in a much shorter amount of time. So where an automotive producer may have allowed 4 months for an RFP response, we're now talking about as low as 2 weeks or 4 weeks to respond. Many of them are facing issues with racing to get certification completed in time. And many of the OEMs expect 80% of the product engineering to be completed at the RFP stage. So I want to give you a brief introduction to SimScale before we get into the details of what we're going to talk about today. So at SimScale, we empower engineers to innovate faster. And we do this by making high fidelity engineering simulation truly accessible at scale to all of the engineers in an organization. Rimac Automobili is one of our customers that has pioneered this type of strategy that we're rolling out to many of our automotive customers. Rimac produce electric hypercars, if you don't already know them, and they have over 40 engineers using simulation at an early stage in the design cycle. So they're really driving that early design stage process to make sure that when they get to the later stages in the design process, they have a mature design. We've got a bit more content to talk about this in more detail. Now, SimScale is a platform for simulation, and it's a next generation cloud native simulation platform. Very much like Onshape is a cloud native platform. We'll come on to the details of Onshape a bit later, but just to position where SimScale fits, SimScale is cloud native. So that means you don't require any VPN or remote desktop to access SimScale. All you need is a web browser, and you can access SimScale from anywhere, just like you can with Onshape. SimScale provides a single platform with broad physics capabilities. This is really nice for an end user because in some simulation tools, if you know how to use the FEA structural analysis, you don't necessarily know how to use the CFD analysis. In SimScale, it's all one clean, simple UI, and everybody has access to all the capabilities. SimScale also operates at any scale, and this is applicable for a few reasons. First of all, you can scale the number of parallel simulations that you want to run limitlessly. So today, for example, maybe I just want to run a simple structural analysis, but tomorrow, maybe I want to run 300 CFD simulations in parallel. I can do that from 1 second to the next without having to enable a special HPC license or speak to anybody at SimScale. Also, thanks to SimScale being in the cloud, real-time collaboration is possible. Just like with Onshape, if you want to collaborate with a colleague, you just share the project with them by entering their credentials, and they both log in and access the same data in the cloud. And SimScale is AI-powered and AI-integrated. We'll come on to this a bit later in the presentation for the done in 60-second side of things. Specifically for the automotive industry, SimScale supports a broad range of use cases. And what SimScale is really great at is putting advanced simulation capabilities, such as nonlinear material analysis for connectors and fastenings, sealings and gaskets type simulations, in the hands of design engineers that wouldn't normally have access to those advanced capabilities in their design tools. Also with heat transfer and CFD capabilities for doing early stage assessments of battery cold plates. That's very much the use case that Rimac Automobile are using to optimize their battery management systems by putting the onus for optimizing the design on the design engineers at the early stage in the process. Also electrical systems with thermal management capabilities and fluid management capabilities. So really a one-stop shop for your design requirements in the automotive sector. Now I've got two more things I want to mention to position what we're going to be talking about today, and really how, with the combination of tools that we're presenting today, SimScale and Onshape, you can address some of the problems that are being faced today by the automotive industry. So I'm really going to double click on that RFP response time and look at that in a fine grain analysis. So the problem that we're seeing is that the simulation lead time can really be a rate limiting bottleneck in engineering processes. I've got a typical timeline here for an RFP process for a tier 1 automotive supplier providing to an OEM. So once the RFP is received, the first stage is to create a new concept design, and that would obviously be the responsibility of a design engineer. Once they've created a new concept, they're going to want to run a simulation analysis to see how that concept works. Now, typically, this requires handing that off to another department to be able to run that analysis. Every time we see the arrow cross the line on the graph here, it represents a handover to a different team, a different engineer. And that usually comes with a simulation lead time. The simulation experts are not always immediately available to be able to pick up that project. So we have a waiting time until that simulation can be started. Once the design engineer gets their result back, they can iterate on the design. And we call this process the simulation cycle time to be able to operate the next design. And that then needs to be simulated again for the design validation. And that requires another simulation lead time. So here you can see in a typical space of time, we've spent a certain amount of time waiting for that simulation lead time to be able to validate our design, and then we can issue our proposal just in time. This process typically allows for 1 to 2 design iterations. And this traditional RFP process has multiple stakeholders from different departments, and it can't robustly support these new, shorter RFP response times that the industry is seeing. So what's the alternative? Well, our solution to this is providing early and broad CAD integrated simulation and AI capabilities. So here we can see an alternative workflow. Once you receive the RFP and start working on it, as soon as that design engineer has a design concept generated in Onshape, they can start simulating it in SimScale. So it really removes that bottleneck of the simulation lead time, and they can iterate through the design many times to optimize the design and get it as good as possible. So here we show on the timeline, we're actually representing the same length of time to respond to the RFP, but because there's no waiting, they can iterate and create a much better design. They still run the final design validation. That's still run by the simulation team, but they are able to issue the proposal earlier with a much higher quality product, because they've actually had time to run many more design iterations. In this example, we're saying 30 plus design iterations. It could be even greater because there's no waiting and they're just able to iterate really quickly. So this more integrated and left shifted design approach really supports the shorter RFP response times. Okay. Thanks. That's enough of my introduction. I'm going to hand over to Nacho now to take you through the Onshape side of things.
Hello, everyone. Thank you, Stephen. It's really great to see how the design process is changing as these cloud-connected tools come into the picture. And with that being said, I want to introduce to all of you what is Onshape and a little bit of why we're here and how it changes the game for people in CAD, and then moving downstream to that simulation process and how we can generate a more iterative environment across the tools. So Onshape is a fully cloud native CAD platform, and it comes with tools that you wouldn't conventionally see out of the box in a CAD tool, including things like PDM. And so you have a full suite of product data management tools that come along with the CAD. There's also collaboration tools that Stephen alluded to with both Onshape and SimScale. You can share others into your design and really get them working with you immediately. And that changes the game to how we can think about collaborating with others and bringing other people into a design process. Finally, we start seeing the ability to do analytics on how our workforce designs and how they interact with each other in a way that we haven't been able to do before. And we're able to scale much faster without the need for hardware. Well, you still need hardware, but you're no longer constrained by these large machines that we've seen in the past, right? If you're a simulation engineer or if you were a CAD engineer, you are used to seeing these big machines that you're working with. As we move to the cloud, we're starting to see a shift away from these things. So you can see on the screen the supercar that's designed by our friends at Pairing. It's an open source car. You should go check it out. They're actually working in Onshape and they're fully designing those cars in Onshape. And I'll give you a couple more examples of our customers as we go through. So this is an intro to Onshape. Stephen, if we can go to the next slide. So just want to highlight how cloud connected solutions really enhance the engineering process across the tool chain and how they bring more people into the picture as we think about engineering. In the way that we think about things, Onshape can sit at the middle, and then we're connected to all of these applications such as SimScale, where we're sort of iterating, right? We're building, we're able to do simulation at the same time as we're doing CAD and really moving through that process a lot faster. So with the CAD design team doing that work, they also will want to bring in other stakeholders, people that are along the tool chain, people that are also working on the manufacturing process, that are working on validating that design if they need to do some other work on that set of components. So what we've seen from people like Ocado is they find that more people come into the process along the time that they spend sharing that data and moving that data without having to share copies and work with all of these sort of painstaking processes that we find when we're moving copies back and forth and operating in these local machine environments. So that's a little bit about how collaboration changes once we go to the cloud, right? And we see that both with SimScale and Onshape, as we move to the cloud, we have more compute, we have more people able to access the information, and we're able to share people into our work much easier. So the last sort of example I want to highlight here, as we are talking about automotive manufacturers, is Garrett Motion. Garrett Motion has been with Onshape for quite a long time. They are one of the largest manufacturers of turbochargers and fuel cell compressors that you'll see out in the market. They're manufacturing parts that go into all sorts of vehicles, from BMWs to anything else you'll see out in the market. One thing that I really love highlighting about the way that they've changed their operations, they moved from CATIA V5 to Onshape, and something that they really experienced was, as they started moving to the cloud, as they started giving people more access to the data that they're working with every day, they saw a much richer group of folk start involving themselves in that engineering process. So as they iterated and as they built, they went from having 200 design engineers to having 700 people get involved in that product design process. To Stephen's point, as we shorten that delivery time and as we bring people closer to the data and the information at that design step, we're able to add a lot more quality to the design that we're pushing forwards into that manufacturing and prototyping step. So really just want to contextualize how this is happening in the real world, and companies like Garrett Motion are seeing cloud native software like SimScale and like Onshape really change the way that they can operate. So with that being said, I want to give you a quick glimpse at what Onshape looks like and present the problem that we're going to be solving today. So in today's first demo that Richard's going to lead, we're going to be looking at that bike handle. I know that this is an automotive design session, but we will be doing a quick simulation on the vibration that this handle experiences. So within Onshape, we designed the CAD and we are fully connected to SimScale. So once we're done with our design, or once we're ready to start thinking about doing some simulation, we can just import that right into SimScale and push any updates as needed. In today's problem, we're actually going to be looking at this handlebar here, and we're going to be looking at the dampening mechanism for the handlebar. So as we approach this in CAD, as a CAD designer, I might not have a very clear idea of how the vibration and the harmonic motion that goes into this handlebar is going to transfer into the real world. So with this model, I'm going to pass it over to Richard and let him show us how SimScale can simulate the vibration in the handle and how we can start thinking about issuing some iterative process into our design toolchain.
Great, thank you, Nacho. And let me quickly share my screen. Exactly. So we're in the first example, we're looking at a bike handlebar, right? And we can assume we have a current design, but in the field, it turns out that there are severe vibrations, right? And now we go into the next design iteration and want to find out, okay, what can we do? What simple design change can we make to really reduce these vibrations? And by the way, that's the same process, right? If you would do it on an automotive part or a bike part, it doesn't change the physics and the problem to be solved at hand. And we had this great model from Onshape, so we couldn't pass this on. And yeah, we're gonna see what could be one solution, and then as we are having this nice iterative connection with Onshape, we can just go through multiple design options and see which one works actually the best. If we have one that goes into the right direction, we can simply and quickly optimize that. So Let's put the case together. So we have these resonances that come either from the motor or from the road into the hand of the people that results in discomfort, fatigue, and maybe even medical conditions if it's over a long time. And yeah, we have an initial design that's not optimal and want to improve it as simple as possible, right? There's some norms that tell you that the vibration should not be higher than 5 meter per second square, and that's what we try to achieve. What options could we have, right? Thinking about solutions that are there already on the market and see which one could fit our use case first, right? When we think about the design ideation step, right? We could use these cone bushings that we have in some situations. In this case, they're really not usable here because we have here a single central cylindrical nut, and we cannot fix that with the bushing that is then made out of rubber, right? It would be just too flexible, and it would not be safe to have this as the single connection between the wheel basically and the handlebar. Another option could be to basically connect or put between a connection of the actual handlebar rods and the central piece bushings, right, on both sides. That's a very, very typical option to reduce vibrations. In this case, it's not really a great solution because these are two separate rods, right? Each is individually mounted to the central piece. That means when we add there, again, these rubber bushings, the feeling of the handlebar would be really soft. So it would be really flexible, and you would feel that while driving, and it would be, doing much more difference than just reducing the vibrations. So what other options could we have? They are simple and not need a full redesign. Another option could be actually to use anti-vibration inserts. So this is a very, very simple solution that could be also retrofitted to existing handlebars, for example. So these are typically made out of brass, and maybe sometimes also have some rubber components and other materials on top to basically add a mass that dampens out these high frequency or mid frequency vibrations to a lower level. So now we have an idea that could work, but we don't know if it actually will work in this situation. So what can we do? Right, we just test it out virtually. So in this case, as I said, we have already an initial design. It was already qualified, maybe not for vibration fully, but we can assume we have an initial simulation that has shown the eigenfrequencies, for example, right? So we can see here the first 6 eigenmodes and see that probably the mode 3 and mode 4 are the ones that are the critical ones in terms of vibrations, right? These are having the horizontal and the vertical vibrations that go directly into the hands. So what are the actual vibrations we're getting? We have, again, assume we have a simulation team that initially validated the initial design, and we have an initial harmonic response analysis done that shows that we have about 7.5 meter per second square peak resonance frequency. Peak resonance acceleration at about 137 hertz, right, where the mode 3 is, and then some later on mode 4 we can also see the resonances there, not quite as high. So, and how a lot of our customers, especially in the automotive industry, work is that there is a template that is made for one specific use case, in this case for vibration assessment, right, that is there, and it's distributed and shared with all team members. And that's now what we're going after, looking at this template and using it on our new design variant and see if that design variant works better, right? Quickly, the physics is very simple, what we're trying to do here. So we're mimicking the road vibrations by adding here a base acceleration, and we're measuring, right, at the positions where we have the hands, we're measuring the response, right? And do that over the frequency range where we have the first 6 to 10 eigenfrequencies. So let's jump right over to SimScale to see how this actually works. So you can see here we're still in a web browser, and what we're seeing here is basically the third eigenfrequency animated. Right? So we can see exactly the deformation that leads to these vibrations that are unwanted and that cause fatigue and discomfort while riding the bike. This is for the frequency, and we have already a baseline analysis for the harmonic response. And let's quickly see how complex or easy it is to set this up. Right, so we have here the harmonic analysis. We added materials to all the parts that we have, mostly aluminum, some steel components, ABS for these parts, and the silicone rubber for the actual handles. That is the initial design setup. And for the load conditions, there's simply this base excitation of 1 meter per second square acceleration, right, that is applied here on the support. And as we have seen already in the slides, right, we have an initial acceleration response for the initial design. Steve will show you later in the more iterative or interactive process how we can bring in a model from Onshape, but it's directly connected. I don't need to upload a file here. In this case, we already have the files available and have them, or the designs available, have them pulled here into SimScale. So the workflow is very similar across all use cases. We use this template and basically just extend it to our new design variant and see if it works better or not than the previous one. So we simply duplicate our simulation. Right, it keeps all the settings as they were. Right, they were defined like this by the simulation expert that has validated that not only the setup but also the mesh settings and everything else is in a way that we can trust in the end the simulation results we're getting. So the only thing that we actually need to do is we change this CAD model for a one that we have already made the changes in Onshape. Right, in this case, we added the brass damper. So change design, we keep the existing contacts and all the other existing settings, and it tells us that the swap was successful. So we could match, right, all settings in the old setup with the new faces or new bodies from the new design, right? And in this case, it's clear because mostly it's the same in just 2 parts. Right here, these brass dampers were added. Now we could simply start a simulation. Okay, not yet. We are prompted here with an error. It tells us that there's something missing, and that is that these two obviously don't have a material assigned because we don't have a brass here. So we quickly go to the material library, we search for brass and add this as a potential material. We want to assign it, and then see if you're done right away. Yes, there's some warnings, but everything else should be fine. And we can run the study and click start. Right, so in this is not a minute, it took a bit longer, but now we have already our first design iteration set up, and we can now wait about 20 minutes until the results are in here to see if that is already good enough. In the same time, as we have already another potential design that has also rubber parts in it, we can just do the same thing again and run the simulation at the same time. Right, as we're cloud-based, we can do this as much as we want. We can run 10, 100 simulations at the same time. It doesn't matter. Our computer is not occupied really with that. So we again change the original one with the brass and rubber one and see if that works now. We keep the existing contacts. We now still add here the brass. We also see that in this variant it's a bit longer to just see if that has also an effect. Again, we assign the brass, and we're now good to go. Not quite. We need still these rubber inserts that you can see here, and we assign them as well material and just simply generic rubber. We don't care now at this point and how stiff the rubber should be, just to see if it has at all a significant impact. Okay, we have material assigned and the rest should be all there, and we're good to go. And we start simulation. Right, so now in a couple of minutes we have checked right? We have assigned a new design, and we need to now wait a few minutes until the results are in. We don't need to do that waiting now because we have evaluated it obviously beforehand. We can quickly go back and look at the results in the slideshow. So here we see already what we call here design 4, right? We can assume that this is not the first iteration, the first design option that we do. The alternative that is already much better than the previous one. We sometimes need to experiment, and maybe not the first idea is the best. So after 4 design iterations, we might be in a place where this design is better, right? And in this case, actually, we reduce from 7.5 roughly to 5.5 meter per second squared, like 25% improvement. That's already great. We still need to go below that 5 ideally. So let's see if the alternative design with the rubber works better even. And yes, we can see that with the rubber, the peak acceleration, the peak RMS of the acceleration is reduced further 44% from the initial design, and we get now a design that's actually below the 5 meter per second square mark, and it passes our criteria, right? And at this point, we could either hand the design back over to the simulation expert that does the full validation study, or the simulation expert is invited into our SimScale project because we can share with all the colleagues in the organization, and they can validate it there, right? They can first check if the setup that I did was correct, and then they could do some more refined studies, do mesh independent studies, or some other things to really ensure that this is the actual response of the system and the design performs as it should. And this was the first case, and now I'm handing over to Steve for the 60 seconds design.
Perfect. Thank you, Richard. Yeah, that was a really nice overview. I think it's great to see how we can get those design insights so rapidly by using the tools connected together. You know, we're talking about minutes to get those results. It could be up to hours in cases, but really eliminating that lead time to get the simulations performed. Now what I want to look at is in terms of seconds. So this is what we were talking about, done in 60 seconds. We're going to be having a look at another part of the motorbike assembly now, and it's the suspension bracket that you see here. So isolating just that part, we're going to have a look at how we can use a machine learning model trained in SimScale to give instantaneous results of what the stress field would be on this bracket, so that you can do those early stage design iterations in seconds as opposed to minutes or hours. So in order to do this, I'm going to be using the Onshape model that we can see here. And I've created a few different design variants. So going from a complete plain concept here to basically an incredibly plain concept with no fillets, just basically defining the overall near net structure for the part, and also looking at including some cutouts in there as well, where we don't need the material. So thanks to the really nice version system in Onshape, we can track all of this and make sure that everything is managed nicely. We can go back through all of the different versions. We've got full traceability over who has done what, etc. So let's have a look at how we can set this up directly in SimScale. So all I've done is change my browser tab to SimScale, and I'm going to start a new project here. So I just need to give that a name and create a new project in SimScale for us to work with. Now, the first thing to do with any new simulation project is obviously import the geometry. And we're going to be bringing this in live from Onshape using the direct plugin that's available. So I can see and browse all of my Onshape models here. I have single sign-on into Onshape. And I can also see all of those versions that I had. So they're all available to me, and I can choose from these versions which ones I'm going to use, etc. So let's have a bit of a story here where we take this simple concept near-net shape as our first import. So I'm going to import that geometry. So this is basically, I'm the design engineer and I've come up with the concept shape for this part that I then want to run the simulation on and gain insights from. So that geometry is brought directly into SimScale now from Onshape. I can see it in here, and I can start to set up my simulation. So I'm going to do this as a static structural simulation, but you can see the full suite of simulation types that I could choose from here for this simulation. And basically now I've got a tree structure to work through and assign my various components to. So first of all, I'm going to assign the material. I'm using aluminium for this assembly, and then I need to set up some boundary conditions. So basically what I want to do now is just set up the boundary conditions for these mounting points. So first of all, I want to define how this bracket is mounted to the chassis. And basically that's going to be free to rotate in the Y direction, but it's not going to be free to displace in any other directions because we're going to say that it's fixed to the chassis. The next thing, again, is to set up another remote displacement here. And this is for the top mount up here, where the bracket fits to the shock absorber assembly on the motorbike. And for this, I'm going to have rotation in the Y unconstrained as well, and rotation in the X, rotation in the Z. Sorry, that's displacement. I'm going to have rotation in the Y and rotation displacement in the Y and displacement in the Z unconstrained. So basically, we're saying that this can displace, but it cannot rotate. Okay, and then the final thing I need to do is set up a load on here. Now the load is coming in on this lug from the wheel, so I'm going to apply a force, and that's going to be on the swing arm mount. And here I've got a force that represents the loading condition that we expect during operation. So we've got minus 1,000 newtons in the X direction and about 3,000 newtons in the Z direction. All of these things can be parameterized, and we can run many simulations in parallel. So that's everything set up and configured. I can fire off a simulation at this point, and a relatively simple structural simulation will take a few minutes to complete. But here we're really talking about how we can get results in seconds as opposed to minutes. So what I've done is I've used my past experience at designing similar components to this, and I've set up a machine learning model in the background that allows us to give instantaneous predictions of what the stress field would be directly plotted on the geometry here. So we can immediately see what the stress fields are, and we have a confidence rating plotted. So based on the data that the machine learning model has seen, we have a high confidence in the results that we're seeing here. So we can obviously start to gain insights from this. We can see that we've got a relatively high stress around this area. So at that point, I would obviously go back to Onshape and iterate my design to start to mitigate for those higher stress-raised areas. So at that point, maybe I would bring in a new CAD geometry where I've added some fillets to account for the stress razors that we saw on those sharp corners. So I can immediately bring my new CAD into the same simulation project. And then all I need to do to get a new prediction of what those stress results would be is swap out my CAD geometry, and I'll get an instantaneous prediction of what the stress results are plotted on this new geometry. And you can see we still have a high stress in this region. We're actually using a different scale here, so we'd have to rescale it. And then we can see that we've reduced the stress in that region by making that design change. And obviously the changes we can make here are limitless. So we can see that there's relatively low stress in the middle of these faces. So maybe we would want to make some further design changes to reduce weight. Weight obviously has a very important impact on the embodied energy of any vehicle. So we might want to change the design here to include some cutouts. We can have a different design. We can go for a plane, or we can go with a design that has a cutout section to reduce the mass of the overall assembly. Again, it is very much a simple process. Bring the geometry in, and you can see in seconds here, I'm iterating through the design. I'm getting design insights, and I'm building up a design over a space of time that would normally take days or weeks, operating with many different people in the organization, handing large files over, and yet I'm able to do everything very easily in seconds directly within the UI. Obviously, we can also make changes directly to the boundary conditions as well. So if I wanted to change the force, I can change that directly in here. So maybe we have a slightly lower force requirement. I can make those changes directly, and I'll see the response for the stress at those lower forces directly plotted onto the geometry again. So you can see that the possibilities are endless, but I'm sure the question you're asking is, how accurate is this? Well, if I swap to my other screen here, you can see a direct comparison of the simulation result on the left-hand side versus the AI prediction on the right-hand side. With the same boundary conditions set up and the same scale bar, we can see a very good correlation between the two results. So the confidence score that we're getting here of 96% confidence really is relevant. We know that we're getting very accurate results based on this model. If we had a low confidence rating, it would mean that the geometry or the boundary conditions are outside of the training data set. All that means is we just need to run some more simulations and plug that data back into the machine learning model, so that next time when we run the simulation or the AI prediction, the machine learning model knows better what our range of data is and can predict the results more accurately. Okay, so thanks for the attention. Let's jump back to the slides for a moment. Thank you for your time. We've got some time available to answer the questions that have come in. So we'll have a look at those, and I'll post some questions to Richard and Nacho about what we've seen. So please feel free to send any more questions in. We've got a few coming through. Nacho, there's one for you here. What are the hardware requirements for Onshape?
Yeah, that's a great question. There is really no hardware requirements with Onshape. You can operate from a mobile phone or a Google Chrome notebook. That we are seeing, like EDU, for example, the students don't really have access to big computers. They're using very, very, very low-end computers, and they're able to do CAD. The only real requirement to operate Onshape is a stable internet connection. 5 megabits is our recommended minimum, but any machine, Linux, Windows, Mac, doesn't matter. No real hardware requirements there.
Nice. Okay, thanks, Nacho. And that's obviously exactly the same with SimScale. There's no hardware requirements for SimScale either. Everything is 100% cloud-based. Okay, next question that I've got here is, Richard, this is one for you to answer, I think. So can the AI model be used for fluid simulations as well as the structural simulations that we've seen here today?
Yeah, that's a good question. Yes, the AI models we're using, they are independent from the actual physics. They're all very data-driven models. We use graph neural networks. Technology behind it is brought by our partner together from Navasto. And you can train any data you have on SimScale. You can train an AI model on that, and then you can evaluate it as well with the same physics. So you can train a model on a structural analysis and can evaluate it there, and one on CFD. Obviously, you will not have the same model that solves for structural and for CFD, but each application can be applied on with their own machine learning model.
Exactly, perfect. Yeah, we've got another interesting question come in. I guess it's related to how Richard and I both presented, and this is kind of an artifact of SimScale. Someone has asked, is this a mesh-free method? Because we saw a meshing icon in the tree, but nothing related to the mesh was explained. That's another really good question. SimScale does use a mesh, but as an end user of SimScale, you normally don't have to worry too much about the mesh. So you will have seen with Richard's simulation, the handlebar assembly, we had a lot of complexity here. This was manufacturing ready CAD. There was not a long time spent cleaning this geometry up and removing features. However, our mesh algorithm was still able to cope with this and mesh it fine to be able to run the harmonic analysis. Richard, did you use any mesh refinement regions? What was your strategy to meshing this assembly?
Yeah, so in this case, I just focused on getting this model as is from Onshape and simulate it. So I obviously could have maybe optimized the CAD to, I don't know, remove unnecessary stuff so I can maybe have a better quality mesh or less elements to get the same accuracy and so on. But this is all was all unnecessary in this case, because we're not that much constrained, maybe as in your local computer or local hardware, that you must optimize for getting a reasonable mesh size. I mean, if it's 5 million cells, then so be it. It might take much longer. And yeah, if I don't want to spend the time, then I spend maybe some manual time of me to clean up the model. But in this case, I used just a standard setup, standard mesh settings, nothing changed. Like we have a scale of 0 to 10, right? Very simple to the user to understand if they want to go for a rather quick turnaround time or for the highest accuracy. And I used the standard 5. But obviously, if you want, right, you can manually define mesh regions as much as you want. You can add refinements, boundary layers, sweep meshing, and so forth. You can all do that if you want to, and if you have the experience to know that, yeah, this actually improves your results and so forth.
Yeah, and I think that's a really good point. With SimScale, we aim for the standard default settings to get you to a good result. But there's always that extra level of detail that you can drill down into. You can open up the mesh settings, you can define specific refinement regions, you can go full manual on it if you want, and define exactly the mesh size that you want to see. In the example case that I ran, it was again just an automatic mesh that was used for the training data, second order elements, and yeah, just very straightforward. The reason why we don't show it in demos is because you don't need to open the mesh. You don't need to worry about it. Okay. a few more questions. I think we've got time to take a couple more. I don't think I'm going to get through them all. If we don't answer all of your questions, don't worry, we will get back to you. But next question is, for multi-physics simulations, can they be trained in AI? And can thermal fluid simulations be trained with AI? So yeah, another question to you, I guess, Richard, about the AI capabilities.
Yeah. So we're going currently through all the analysis types you're having. So Steve has shown you in the simulation setup, we have about 13 different analysis types. Although the method itself is agnostic, you just need to still enable the process, right, that these results are understood and can be trained. So currently we're actually working on the conjugate heat transfer analysis that will be enabled toward the end of this quarter, beginning of next quarter. And then you can really train coupled fluid thermal analysis with the structure and the fluid inside, predict the pressure and the velocities in the fluid, but also the temperature distribution in the solid, for example.
Okay, great. Another question about the machine learning model. So the next question is the algorithm for the machine learning model chosen by the user, or is it decided by the software automatically? And what are the available algorithms, and can they be tuned? So in answer to that, we have partnered with Navasto for this machine learning model. It is a graph neural network that's running. And if you want more details on this, I would recommend that you re-watch our Sim Copilot presentation, a webinar that we did a month or two ago that goes into more detail on the AI algorithm. But for brevity now, it's provided by Navasto, and it's a graph neural network that's incredibly easy to set up. We take care of all of the complexities. Okay, I think we've got time for one more before we go to the closing remarks. So there's another question about Onshape and about how the connection to SimScale works, Nacho. So the question is, how is the model imported from Onshape to SimScale? Is there any copy created locally?
So the way in which you're connecting from SimScale to Onshape is through your logging, right? So you're going to be able to connect your Onshape account right from your SimScale account. You'll be in SimScale, you'll log into Onshape, and then you'll be able to pull data from your Onshape environment into your SimScale environment. So there's no need to download any sort of parasolids or steps as you might do in a more conventional environment, and then re-upload those. And as Steve demonstrated, there are some really massive benefits in the way in which that allows you to update the parts that you're simulating, because you won't have to rerun the entire simulation on an updated part. And that allows you to iterate a lot faster because you're just pulling from the Onshape document. The way that Onshape deals with data, as Steve showed, is with these versions that we're sort of tracking through. So you're just pulling from the container of data that Onshape is hosting the parts in, and that's what we would call a document. So there's no local copies along the process. You're just signing in and you're establishing a connection between the two applications, and you're able to work through.
Exactly, thanks. And also, if you want to get geeky about CAD kernels, SimScale and Onshape actually work really nicely together because they both have a parasolid CAD kernel. So there's great compatibility. You never see a situation where you bring something in from Onshape to SimScale and you have parts intersecting that shouldn't be intersecting, or unwanted sheet bodies, etc. There's excellent compatibility between the two tools.
Sure.
Okay, great. There's a few more questions, but I think we're going to have to leave it for now. We'll answer those in the follow-up because I just want to give enough time to this final next step slide. Really, this is one example we've showed today of how connecting up these two powerful tools can help you to meet shorter RFP response times. If you want to get going with SimScale, you can sign up now by going to simscale.com/sign up. You can request a demo directly. You can contact us directly at sales@simscale.com. You can contact me or Richard through LinkedIn. There's many ways that you can get in contact with us. Please do reach out and we'd be very happy to help you get going. Also, Nacho, if you want to cover the Onshape side of things as well.
Sure thing. Thanks, Steve. So Onshape is free for everyone for 6 months. If you're a professional looking to evaluate a new CAD system, or if you just want to give Onshape a try to see what it's capable of, it is free for 6 months for anyone. If you're a startup and you want to get Onshape into your startup, we have startup programs that are a little bit longer lasting for people that are getting up and running, and those are also free. Feel free to, as Steve said, find me on LinkedIn or just scan the QR code that will get you on your way right now, or you can reach out to Kieran Murray, whose email you have there. He's one of our head of sales, so he can get you more information. So thank you.
Perfect. And just one final closing remark. There's a couple of questions been asked about the recording. Of course, we will make the recording for this session available to all registrants and attendees. There will be a follow-up email, and we'll also include in that the simulations and CAD that was used in the session today, so that you can have a deeper dive into it and have a look at it yourselves. All right, thank you very much. See you next time. Bye.
Thank you.